Welcome back to the second chapter on how to set up neural networks for architects, day 4, chapter 2. We want to go for training networks. Last chapter we set up, we'd seen that there's a huge library of different kind of layers, and we can combine these layers to a kind of production line of doing things. But that's not the story of neural networks, because these are just functions. Neural networks is, with encoders, you put these things to the edge of the world. So from the edge of the world you take a picture, then you start to rationalize it and circulate these things in time, you observe, and then you talk back with decoders to reality. So this chapter now is on how to train a network. So it's very profound to talk about that as learning, because I think it's exactly not learning, because aliens don't understand. So it's misleading, all these storytelling around that. It's very important, I think, to make this distinction. So there we can start with with a single number to learn. So the most simple thing. So all this story is like this. So instead of going for a production, you say input, function, output, production, output. It's that you have two different perspectives. You take two different perspectives. You take the input perspective and you take the output perspective. And you say they are the same. And this is not arithmetics anymore. This is algebra. And algebra says here, what is it? Algebra, the joining of broken parts. So you say whatever it is, input and output is of the same. So you don't touch the same. So in these pairs here, you see, the same is just an addition of 0.1. So we want to learn that. So without touching it, anything. So this is the same with that the perspective drawing is the invention of Renaissance, which is of similar importance. And it's algebra as well. So, and therefore, you have to sit at the edge of the world, which is this point, the perspective point of infinity. And you say, whatever I see in reality, it's of the same. So you kind of forget it, and by that you get a rational view of the thing. You say, all this is the same in a certain mechanics. So, and this is a perspective drawing. So you have all these points of reality and you say it's the same. Or you can, for example, say this is reality and this is my point in drawing. And they are the same, algebraic the same. And by that you can do these crazy new virtual things only aliens can do. So it's very important, it's algebra, it's not arithmetic, it's not an algorithm. Implementation of that is an algorithm, but it has to be thought as algebra. So it's not, therefore, it's not about intuition. It's about what you can imagine as the same. And you take different perspectives to the same. Input and output is, again, it's not the proper way to describe that. It's just one eye and the other eye, and the difference is what is space. You cut it 2 times, and the difference of these two perspectives is what you do with intelligence as space. Algebra. Good. How to do that? Go here. If we go with graphs, it's always not working properly unfortunately in the cloud. What we have here is, let's have a look to the graphics. We have an input. This is of a vector of size 1, a single number. So we have here a threading layer. We just add input 1 and input 2. There are two input ports to this. We need 2, and they are of size 1 and of size 1. And we simply make a plus, pairwise plus to these numbers. And put that to our output, which is the input here, and then input is inherited from here, and it puts it to the output, which is our specification here. I think we can leave that because this is automatic, can be automatic, but this is a specification of the input. So what we have here is something internal, and that's a value, an array containing a number which is not an input. So, and we said it's a net array layer, and it's one-dimensional, and the initial value is 0.5. So that's here, net array layer, array, it's here of 1.5. So what we do here is input is added with 0.5 and put that to output. So, but this thing is trainable, and that's a new element. By that you are at the edge of the world, it circulates whatever is coming. So it make a ratio about whatever is passing by, or what you take a perspective to the world. So how is this? Does it run? It's here. This is how to access these things. The net is here. That's the net. Go for 1. It's here. Arrays. It's here. And go then in with array. So here, this is here. Path. It's array 1. Therefore, you enter array here. Get that, and then you have 0.5. So which means if you run our net with a 2, it's getting 2.5. So next step, that's the production line we knew before. So with the next step is we take these samples of an 0.1 to add, and we expose our machine, our network, to these two perspectives to the same. This is what is training. Just to contract these two sides, so to get a rational understanding, for example, of the space. So you have one eye, another eye, and you contract that to get an idea of space. So it's a contract between the two eyes. And it's the same here. Contract between input and output, unfortunately named like that, and you say it's the same idea. So what we have now is, of course, the same thing, but we can ask for our value, normal, extract. Now it's net, the trained net, so we have to put it here, and then this array is 0.1. So it's adapted because of this equation, of this equality. So he learned what is to understand with this sequence of equalities. So therefore, if you put a 3, and there is no scree here, it just says it should be 3.1 because it got the idea, whatever it is. So it's very robust against errors. Yeah, for example, you can say if you have 1.7 and train this. So now there is an error. So it doesn't matter. So there's no regularity. Nevertheless, now we have a certain value here, and it makes some reason of it. Good. There's no problem with imprecision, incompleteness, no problem with contradictions and so on. All this, forget it. You are alien, you're not touched by contradictions or imprecision because you have no senses. So that's the first chapter, training. Now the algorithm, how to train. So again, there's a lot of, look at this. a lot of explanation and intuition to make it intuitive how backpropagation works, how this learning works. De facto, I think there are 100 different ways how to do that. In Mathematica, you have some 10 at hand. So, and they do it by default and try to find the best. All this is within the package, so you don't have to care about. The important thing is to look at it, but there is no reason to understand it. It's not about intuition. You are at the edge of the world, and it's about imagination. It's not about intuition. And imagination is talking. You have to be able to talk and not to see and to sense these things. Therefore, it's misleading if you try to understand how it works. So, and de facto, it's super diverse how these things are, and there is no principal mathematics behind it. Don't forget this idea that there's one consistent model how this is done. There's a lot of different competing ways how to think about it. So what I think, and what is very rare in this, it's just this idea. So it's because it's not a function, because it's not a production, it's not an algorithm, which is important. It's just that the function of an input equals algebraically the output with errors and whatever. So which means you have to minimize the difference between inputs and outputs, or if you say the function of the inputs minus the outputs should go towards minus. That's called backpropagation. So there are illustrations and all around, and to show you how this works in Mathematica, I have this intuitively understandable 1- and 2-dimensional case, and you have to imagine that with 1,000, with a 1,000,000-dimensional space, so therefore it's getting so crazy, but it's just this kind of talk. So this, for example, is a function with a lot of minima. So we have a minimum here, you have it here, and you have it here. So now we say we want to differential evolution. You see these are the methods you can find. You can look it up how it works. This is a function x, we defined it here, and we go from -7, so it's from here, not to have this minima. This is a minima, local minima, this is the absolute minima, and we go with +7. So we ask for the minimum, and we find it at x 5.9, which is here, and -3.1, which is here. So this is how in Mathematica a minimum on a function is done. So if you want to see that, let's make it, or it's better in. So you see how it is working. So it's an iterative process. So it's looking around all these things and gathering, and then somewhere he finds these points, and then it's going here and finding its point in a certain precision. You can't find it an absolute point with these kind of functions. So this is an interactive version of that, how it's working. So now you see how these iterations work. So it's jumping around, scanning, and then after some iterations it knows it must be somewhere like here, and if you go then with some 200, you are there. It's enough. Yeah, somewhere he stops with certain resolution. So this is how the backpropagation works. You simply take the input, get the whole network as we set up as a production line of functions with these parameters to train. We could put that, for example, our our single parameter, and change this parameter in a way that the input with the function produces equals algebraically the output. And then you have to find, you have to tune the minimum of this parameter, this hidden memory element within the network, so that the things algebraically are the same. So that's how it works. So this is talking about it, not like all the others try to show it. So this is a two-dimensional case. It's just the same, the same setup, and you can do it. You can do these things. Look it up if you are interested, and make it for 5, for 10, for 12 dimensions. It just works like this, but you can't make it visual. This is a two-dimensional visual thing, and has the same mechanics as we had it in one dimension, so that you believe that it's somehow working. Finding the minimum. Good. That's backpropagation. It's a mechanism. So, and a neural network is built with, mainly built with linear layers. There are convolution layers and so on, but the linear layer is the mother of all layers, which means you have input ports, you have output ports of a layer in multi-dimensions. In this case, for example, we have an input of 3 ports and we have an output of 2 ports, and then each input is connected with each output, which means in this case, this is called linear. We extract that. So we go arrays, weights. We have that, arrays, weights, and then we can ask here, and we have 6 variables. So this is input port 1 to output 1, input 2 to output, and so on. This is the multiplication part of it. And then with the biases, you have the addition part of it. These are the biases, and currently they're default. This is random. Default, there is nothing. So if we get a vector, 3-dimensional, we need 3, it's here as well, then it produces this output, a 2-dimensional output. And it has 6 plus 2, 6 multiplication, and 2 additions, so that, 2 values to add, and 6 parameters to multiply. With that is adaptable. This is the instrument this neural network is able to equalize inputs and outputs. So it's very low resolution. So to see how this is, that's how the production line of it is working, take the biases plus the weights, dot product the vectors, and then you see it's the same value. If you want to see how the dot product works, you have 3 inputs, 2 times 3 inputs, and then the vector, and then this is how it's done. Look it up with dot product to understand what this operation, basic operation is. And this operation, which can be done with the GPU, the graphic processor. These matrix operations are super fast, and this is with computer graphics. And by that, neural networks are so powerful and so fast. So this is the linear layer, the very basic layer. So now there's a scheme to finish this this chapter. There's a scheme how to make to build a neural network. So let's go here. First, we need a lot of samples. So we need a lot of data, inputs and outputs. So to simplify our life, we don't do it by hand or take photos or whatever. We simply have a function. I say it's a batch function, and this batch function can create samples. In this case, we have random integers from 0 to 10. This is here, 0 to 10, and then the input is 2 numbers, and the output is the addition, the plus of these 2 numbers. 15, this is 6, this is 5. So we need samples, and in this case we do it very simple, just with a function to be fast. So then we have to distinguish 2 different sets, batches. We have one to train, so where we calibrate the neural network. So the neural network is reasoning about, no, it's putting things into differences and and thinking about that and talking about that. And we do that with a set of samples, and we test the resolution and the precision of the clearness and the correctness of that with a smaller data set in most cases, which is not part of the training set. So then it's not corrupted. So of course, if they learn and seen certain scenarios here, they know, and then it's just precisely that. So this validation set is always not known and not trained. So to get a good measurement of how good the network works. So that's always the same. So this is always a third step. So create a network. In our case, it's just a chain, linear layer, two-dimensional, linear layer, one-dimensional, have these kind of connections. Input is two-dimensional, we have it here. The output is one-dimensional, vector, it's here. So if we have that, we can see it here, the linear layer, check it, all this is done. Very simple. So we can check the first layer's weights. So this is the first layer, weights. This is 4. Second layer weights, this is 2. So we have 6 weight parameters, and then we have 2 and 1, I think, and we have 3 bias parameters. So it's in total there's 9 parameters, not more, to train. So our network has random initial values. So therefore, an addition, he says, an addition of 3 and 4 gives this. So nonsense, yeah, random stuff. So now we expose our network with, that's the fourth step. We expose our network to the training set. We say we want to have all parameters to check the quality and the training. And then we say our validation set, we want to qualify our result should be data V. These are the 2 sets we had here. So that's the first step. And we simply do this here. So you see, this is the Adam optimizer. That's the, in this case, this is the back propagation. And this really goes to 0, yeah? You see, we can stop it if it's so. Inspect this, because we had it here with the training. Where's the training? Here with all. Then we can inspect. We can have the loss plot. This was a plot, the measurement of the quality, and we can get the actual network. This is what we started with to train. So the loss is towards 0, and that's it. So now step 5 is run it. So it's very clear now. We take any kind of numbers. It's at this 4 to 6, and this is an example. If we just want to have the input, so we ask for the second perspective and ask our trained network, which is this one, not T. T is just the summary of the training process. If we have this, put in here 4.2, that's this, or if we simply take any kind of number, it should work. We have 2.4 and 4.2, it should be 6.6. So you learned an addition without talking anything about functions and just by algebra. fixing broken bones. So fixing two perspectives to the world without touching the world, by only picturing the world and then talking about it. Good. We will go next chapter. We will go. There are two different applications of neural networks. One is classification. We call that differentiation. We will have a super simple chapter on that. We classify numbers. We will see how this is working. And the other is called prediction, and we call that contracting. So, because if you're outside, stories are different. The games are different. So these will be the next two chapters to discuss the two principal different applications we are running in with neural networks on a very basic level. So thanks for watching, and see you in the next chapter.